Alright, gang, here we go. This is for Chem 1, Unit 14, Part 2. We're talking about Le Chatelier's principle. Alright, so we just finished talking about equilibrium and what that looks like when we have something at equilibrium. Remember, if a system is at equilibrium, that means it has two opposing reactions that are equal and opposite. One is the forward reaction and the other one is the reverse reaction, and they are both happening at the same time, and so the reactants are making products and the products are making reactants, and they go back and forth. And remember, when we reach equilibrium, that does not mean that we have equal amounts, but it does mean that we have equal rates in the forward and the reverse reaction. Okay, so when we're at equilibrium, we've reached this sort of balance. Okay, and this balance that we've reached is really an equality of rates, right? Because once we've reached that equilibrium, the amount of reactants turning into products, the number of products turning into reactants are equal to one another. Those two rates, all right? And so we can do things to disrupt this balance, okay? And so imagine, so essentially we're adding what are called stresses. So if we stress that equilibrium, Le Chatelier's principle says that the equilibrium will respond in order to counteract this stress. All right, and we call this the shift. All right, so it can shift one way or the other, either towards the reactants or towards the products. All right, so here's the Chateliers principle in fancy chemistry words. It says, if a stress is applied to a system that is at equilibrium, the system changes in a way that relieves that stress. So imagine, you're coming back from summer vacation. We're not too far off from summer. So you imagine yourself coming back from summer vacay, and you've reached equilibrium. Maybe you sleep until noon every day. Maybe you have to get up for a summer job. Whatever the case, you've reached this summer equilibrium, and then you go back to school and you have a teacher, a chemistry teacher, and that chemistry teacher says, all right, you're back at school, time to start learning again. Here's some homework, here's an upcoming quiz or exam, etc., etc. All right. So, and so you've got two choices. You have to respond to that stress in some way. Either, number one, you start working hard enough to counteract that stress so you still get the grade that you want, or you just drop out of high school, right? And so, obviously one of those is a better choice than the other. And, but regardless, your equilibrium has been stressed, and then you've reestablished equilibrium by adapting to that stress, one way or the other, good or for ill. All right. So we're going to talk about three different stresses in this video. We're going to talk about changes in concentration, changes in temperature, and changes in pressure. All right, changes in concentration. So the big thing here is just think about this in terms of reaction rates. Okay, like we did before. Remember, if we're at equilibrium, that means our rates are equal to one another. So if we have this reaction here, A going to 2B, or A plus 2B is in equilibrium with C plus D. All right, this is our equilibrium. So we're at equilibrium. A and 2B are reacting together to form C and D, and then C and D are reacting together to form A and 2B. All right, and so we've got this reaction. We're at equilibrium. The rates are equal to one another. All right, but if we added one of these substances to give us more concentration, like for example, if we had A and we increased the concentration of A would be hitting B more often, right? We talked about reaction rates, and we talked about how we can increase concentration in order to increase our rate. And so if we increase the rate of these two guys hitting each other, our whole reaction is going to speed up. On the forward side, the forward reaction is going to speed up, so we'll shift to the right. Okay, you can kind of imagine this as kind of like playing tug of war, but instead of playing tug of war, it's really kind of like playing like a push of war. Okay, and so you've got your forward reaction and your reverse reaction, and they're pushing against each other. And if you do something to disturb that rate, essentially what you're doing is changing how hard it can push. So, for example, like if we add one of the reactant side, then the forward reaction is going to start pushing harder. So we're going to end up shifting towards the product. So we say that would be shifting to the right. And if we add a product, then the reverse happens, right? Our C and D would be going to the left, right? Our C and D would end up pushing harder because once we're at equilibrium, they're pushing equally hard. But if we add C or D, they're going to start pushing a little bit harder. So we're going to shift towards the reactant side. At the same time, so that's if we're adding reactant or product. We could also go backwards, right? We could also, so well, what if we introduce something that lets one of the things go away? So imagine that as we're forming C and D, we let D escape. Okay, so as D goes away, the C and D never reach equilibrium, right? So we're just going to keep going to the right. So what if we've got a system at equilibrium, and then we take away some D, all right? And if D leaves, then that reaction pushing towards the reverse reaction, going back towards the reactants, well, that'll slow down. So that means that'll get less strong, and so your whole reaction will shift to the right. And then the same thing happens on the reactant side. It would start pushing less strong, and you'd shift towards the left. All right. So just to recap, generally this is kind of where we're at. All right. Now, I think personally, I always err on the side of just thinking things through. I hate memorizing. Okay, so I'd much rather just think about, like, well, what's logically, how does this make sense, as opposed to, well, what can I memorize? But really, you could just memorize this table and you'd be good. If we increase the concentration of a product, we shift left. If we decrease the concentration of a product, we shift right. If we increase the concentration of a reactant, we shift right. And if we decrease the concentration of a reactant, we shift left. All right, now, Le Chatelier's principle, let's practice this, okay? All right, we're going to say we've got this reaction, PCl5 is in equilibrium with PCl3 and Cl2. If we add Cl2, what does that do? Which way will we shift? So if we add Cl2, this chlorine will react more often with the PCl3, so our reaction will speed up in the reverse reaction. So going from the right side to the left side will speed up, so we'll end up shifting to the left. Okay, maybe shift left. All right, now if we remove PCl3, that's this guy here on the product side. If we remove PCl3, the reaction going to the left will slow down, okay? And if this slows down, then it'll push less hard, so we'll end up shifting to the right. All right. You could also just use the same table here, right? We increased a product, so we shifted left, and then we decreased a product, so we shift right, okay? Next thing we could do is change the temperature. All right. Now the trick here is to first identify whether you have an endothermic or an exothermic reaction. Remember, if our enthalpy change is positive, that means we have an endothermic reaction, and if our enthalpy change is negative, we have an exothermic reaction. Okay, so if it's an endothermic reaction, that really just means that we need heat in order for our reaction to proceed in the forward reaction. So that means heat would act like a reactant. So if you have an endothermic reaction, just treat it as a reactant. If you have an exothermic reaction, just treat heat as a product. Okay, and that makes sense. Okay, so let's think about this real quick. So change in heat is treated like change in concentration. As soon as you have established whether you're endothermic or exothermic, and you put it as either a product or a reactant, life gets really easy, and you can just think about it the same way you just thought about the concentration changes. All right. So in this specific case, we have an exothermic reaction. A and B are reacting to form C and D and producing heat. Right, it's exothermic reaction. If this reaction is heated up, then the reaction shifts to the left. Right. This is technically at equilibrium. This is not a reaction error, but it's shifting. Anyway, so we're going to shift to the left because we're increasing the concentration of a product. All right, let's try this guy. What effect does this have on the equilibrium position? So we have PCl5 plus heat. So this is an endothermic reaction because our heat is a reactant. So if this is our reaction, PCl5 plus heat is in equilibrium with PCl3 and Cl2. We increase, so it says we remove heat or decrease the temperature. So we take this container that all of this is going on in and put it in like an ice bath. This heat will go down. Okay, and so therefore we're decreasing the concentration of reactant, so our whole reaction is going to shift to the left. All right, so we shift left. All right. Changes in pressure. Now this, in my opinion, is the most confusing one, but let's give it a shot. Okay, first of all, changes in pressure only affects gaseous equilibriums. Okay. They only affect gaseous equilibriums. And that makes sense because pressure only affects gases, right? It doesn't affect solids or liquids. All right, so or aqueous solutions. We only care about if we have gases for our pressure. Okay, and now not only that, but we need to make sure that the number of moles of gases on both sides, moles, and maybe we should put in this of gases, all right, are unequal. So let's look at this guy. Let's assume our hydrogen, nitrogen, and ammonia are all gases here. All right. So how many moles of gases or how many molecules of gases do we have on the reactant side? Well, we have 4. Right? We have 4 if we assume all of these are gases. 3 hydrogen atom molecules and 1 nitrogen molecule. So we have 4 gas molecules on the reactant side. On the product side, we have 2 molecules of ammonia. Okay, so first thing you do whenever you see you have an equilibrium and you're changing the pressure, first thing you need to do is go through and make sure that you count the number of moles of gas on both sides of the reaction. Now remember to look only at gases. Sometimes you'll have gases mixed with solids or liquids or aqueuses. Only look at gases. That's the only thing that matters when we're talking about changes in pressure. All right. Now generally these are our rule of thumb. If our pressure increases, our equilibrium will shift towards the side with less gas molecules. Okay, so here, if we have this reaction here, we'll shift. If we increase the pressure, remember this means this whole thing is in a container, right? If we shift towards, and once again, this should be an equilibrium arrow. If we increase the pressure, this whole thing is going to shift towards the right. Now think about it this way. If we increase pressure, what does that do to the concentration of the gas? Well, the concentration would go up because that's the same number of moles in a smaller volume, right? So the concentration goes up if we increase pressure. So if we increase concentration of these gases because their pressures go up, that's really the same thing as what we were just talking about. So we know if we increase concentration, the rates are going to increase. So then really it just becomes a competition between the two of which one is going to have a bigger effect from the concentration increase. Well, the one that has 4 gas molecules is going to increase more than the one that only has 2 gas molecules. Okay, and so the reaction rate or the reaction is going to shift towards the right side here because there are less molecules, so that's the one that's not going to speed up as much. All right. Decreasing in the pressure does the same idea. They're both going to slow down because their effective concentrations have gone down. All right, so because they both have lower concentrations, the rates will go down on both of them. All right, but the one with 4 is going to go down more drastically, so it's going to shift to the left. Okay. So here's a little picture diagram to help you kind of think about what's going on here. You've got 2A is in equilibrium with B. All right, if we decrease the volume, that's the same thing as increasing the pressure, right? Our volume is about half of what it was before. All right, and notice here that we've shifted towards the sides with B and away from the side with A. All right, so our new equilibrium is going to favor the products because it's got less total moles of gas. All right, as we increase the volume, the number of moles of gas is going to increase. Okay, and so we're going to go to the side with more moles of gas. All right, and once again, we've increased volume, so they're more spread out, so our pressure has gone down. All right, so here's a big old follow-up kind of thing going through everything. So we've got this reaction, carbon solid plus water. Gaseous water plus heat. So this is an endothermic reaction, is in equilibrium with carbon monoxide gas and hydrogen gas. And we want to predict the shift from each of these 4 changes. So if we increase temperature, what happens? Well, if we increase temperature, the reactant side of the forward direction has the heat in it. It's an endothermic, so the forward is going to get faster, and the products doesn't change. So we're going to shift to the right. All right, the next one is if we increase the pressure. So remember, whenever we see this word pressure, that means count the number of moles of gas. So on the reactant side, we only have 1 gas. That's a solid, and that's not anything. So we got gas, all right, 1 mole of gas here. We have 2 moles of gas here. So if we increase the pressure, concentrations go up. Which side is going to have a bigger change in concentration? Well, this side is because they have 2. So we're going to shift left. All right, now what happens if we remove hydrogen? Well, if we remove hydrogen, hydrogen's over here. If we remove hydrogen, the concentration of hydrogen goes down. All right, and if the concentration of hydrogen goes down, then that means this reaction in the reverse reaction is going to slow down, so we're going to shift to the right. All right, I'm not going to write shift just to shave time here. Shave time. I'm Sean Connery all of a sudden. All right, addition of water vapor. Okay, we add a reactant here. that means this guy's going to increase in the forward direction, so we're going to shift to the right. Right? So anyway, so do your practice problems with these. They're not too bad. It is kind of tricky to think about them in terms of reaction rates, right? But be able to predict your changes and all that stuff. So do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.